Water containing 5 grams of dissolved sugar per litre flows into a tank at a constant rate of 6 litres per hour. Water is drawn from the tank, initially containing 240 litres of water with no dissolved sugar, at the same constant rate of 6 litres per hour. Let the weight of sugar in the tank after T hours be W grams, and assume the sugar is always evenly dissolved throughout the water in the tank. By considering the rate at which dissolved sugar flows in and out of the tank, show that dW dt is 1200 minus W over 40. The water drawn from the tank can be used during a manufacturing process once the level of dissolved sugar exceeds 0.5 grams per litre. Derive an equation for W in terms of T and determine how long this will take. So let's consider the situation in part A. Let's say that this is our tank. And remember, initially that contains 240 litres of water that has no dissolved sugar in it. And then we start pouring in our sugary solution. 6 litres per hour, and each litre has 5 grams. And therefore what we're doing is pouring in 30 grams per hour of sugar. We're also drawing out 6 litres per hour. Now, if at some time the mass of sugar in the tank is W, and we know that there's 240 litres in here, the concentration would be W divided by 240 grams per litre. Flowing out of there is 6 litres of that, so that would be 6W over 240 coming out each hour. So the net flow, dW dt, would be 30 coming in. Take away the 6W over 240 going out. 6 and 240 cancel to give us W over 40. And then if we put that over the common denominator of 40, we get the differential equation that we want. Now, before we move on, let's just remind ourselves what we want to do in part B. The water drawn from the tank can be used during a manufacturing process once the level of dissolved sugar exceeds 0.5 grams per litre. Derive an equation for W in terms of T and determine how long this will take. So we have this differential equation, and we need to go ahead and solve it. It's a separable equation, so we could separate it like this and leave the 40 on this side. Remember to use the reverse chain rule here. You've got a negative W, so it'll end up being negative log 1200 minus W is T over 40 plus a constant. So just multiply through by negative 1, and I've written 1 over 40 as 0.025 as well. I didn't change the sign on the C because the C is an arbitrary constant. Taking the exponential function of both sides gives us this. And we can use our usual technique of splitting e to the negative 0.025t plus c into e to the c times e to the negative 0.025t, and then making e to the c a constant. I mentioned that I would shortcut that process in an earlier example. W equals 0 when t equals 0. And that gives us that A is 1200. So 1200 minus W is 1200 e to the negative 0.025t. And we can rearrange that to give us W equals 1200, take away 1200 e to the negative 0.025t. And we could even factorize out the 1200. Now we're interested in when the concentration in the tank reaches 0.5 grams per litre. So remember that the tank is 240 litres. That means the total weight, W, would be 0.5 times 240. And we just need to solve this equation. So 120 is 1,200. 1 take away e to the negative 0.025t. And dividing both sides by 1,200 gives us this. And rearranging, that tells us that e to the negative 0.025t must be equal to 0.9. Take the natural log of both sides. Remember that the natural log and the exponential function are inverse functions. So the left-hand side just becomes negative 0.025t. And then t would be the log of 0.9 divided by negative 0.025. And that gives us 4.214 hours, or if you like, approximately 4 hours and 13 minutes.